Let's talk about cyclic molecules. In terms of the naming, the same type of pattern, the same type of technique applies to cyclic molecules. The only thing that's different is that in addition to naming your alkane or alkene or alkyne, you have to use the prefix cyclo if the structure happens to be that of a polygon. And by that I mean you have a 5-member ring, a 6-member ring, 4-member ring, any type of ring structure that will have to be present with the prefix cyclo. Alright, so there's a few things that we need to take into account and a few rules that you're going to have to keep in mind when naming molecules. The first thing is that when you do have linear segments as well as cyclic segments, if one of the two, and by the way, you only have one linear segment and one cyclic segment, so this is very specific, so only one ring within the linear segment. If the linear segment has more carbons than the cyclic segment is the substituent. However, if the cyclic structure has more carbons than the linear chain, then the linear chain is the substituent. So here the parent chain will be the blue segment that you see here. Your cyclopentyl is going to be your substituent. Over here you have 5 carbons in the cyclic ring, but you only have 4 carbons on the linear, so the linear is your substituent. So this will be your butyl substituent on your cyclopentane. Right, so as far as naming goes, this is 1-butyl cyclopentane. This right here, if you count the atoms, 1, 2, 3, and 4 versus 1, 2, 3, 4, 5, you go with 4, the lowest value. This is 4-cyclopentyl octane, right? 8 carbons altogether in the blue chain. All right, this is the most straightforward case. But as I stated, only one ring per chain. If you have something a little bit more of a gray area, like the example right here, notice that we have a 5-member ring, so 5 carbons. Notice the chain right here, the linear chain has 1, 2, 3, 4, 5 carbons. So you have 5 carbons on the ring, 5 carbons on the chain, only one ring per chain. And over here, same idea. You have 1, 2, 3, 4, 5 carbons on the linear chain, 5 carbons on the ring. So this is a neutral case. What you do is the parent becomes the one that has the most substituents. So looking at these two molecules, notice that the cyclic ring has the methyl substituent and it has this other thing, whereas the linear chain only has the cyclopentyl substituent. So the ring in this case is going to be the parent chain. But over here on the right side, the cyclic chain only has one substituent sticking out of it, whereas the linear chain has the cyclic ring and this methyl group sticking out of it. So in this example, the linear chain is the parent chain. And in this other example, the cyclic chain is the parent chain. So this will be cyclopentane, whereas this one will be regular pentane as the regular name. In terms of substituents, this one has 1, 2, 3, 4, 5 carbons in it. So this will be a pentyl substituent, but it's attaching through the second carbon. So what we do is we name these things alphabetically. So methyl comes before pentyl. So we say 1 pentyl, or excuse me, 1 methyl. And for the pentyl, we simply say if this is position 1 on the ring, this is position 2. And since we're attaching through the second position of the pentyl substituent, we have this 2' segment telling us the attachment is through 2' in the molecule. Here it's a little bit more simplistic. We have pentane as the parent molecule, and sticking out of pentane we have cyclopentyl and we have methyl. Cyclopentyl comes first alphabetically, methyl comes last. So you pick the numbers that you have the lowest value, right? So 2 cyclopentyl, 3 methyl versus 3 methyl, 4 cyclopentyl, right? So that's what you want to have in terms of your names. And in cases where your linear chain contains more than one ring, automatically the linear chain is the parent molecule. So here you have 1, 2, 3, 4, 5, 6 carbons. Here you have 1, 2, 3. And this is irrespective of the sizes, right? So having more than one ring changes the picture altogether. The rings become automatically substituents. So 6, you have 2 cyclobutyl rings, and here you have 2 cyclopentyl rings. So this becomes 1,4-dicyclobutyl hexane, and this one is 1,3-dicyclopentyl propane. Okay, one more thing to talk about, substituents in cyclic structures. Here you could encounter some cases that are a little bit ambiguous. So notice this cycloalkane that we have 5 carbons, so it's a cyclopentene to be exact, and we have 2 chloro substituents present. So when you name this, you will say dichlorocyclopentene. Now, how you number these things? Well, the alkene is the functional group, so you have to give the lowest number to the alkene. But there is 2 ways to do that because this is cyclic. This could be position 1 on the alkene, which makes that position 2, and then 3 and 4 and 5, which means that your chloros are positions 2 and 3. So this is 2,3 dichloro 1-cyclopentene. And the 1 because that's where the alkene first appears. On the other hand, you could start the other way around. Still make the alkene the lowest value. So this end of the alkene is 1. You go to the other end of the alkene, that's 2, and then work your way around the ring. And when you do that, chloro is now position 1 and position 5. So the structure now becomes 1,5-dichloro 1-cyclopentene. And here you want to ask the question, well, how do you determine which structure is the correct one? They both have the same value for the functional group, the alkene. So that doesn't really tell you anything. So it's going to come down to the substituents, the chloro substituents. And notice if you compare the top segment to the bottom segment, 2 becomes 1, that's good, it goes down. 3 becomes 5, that's bad because it's going up. So you have one good aspect and you have one bad aspect. It's technically neutral. You're not really changing anything. And whenever this happens, when it comes down to the substituents to tell what naming is going to prevail, and you end up with a neutral case, same number of good signs as the number of bad signs, you choose the structure that has the lowest number first. And that means that between 2 and 1, 1 is the lowest number. Therefore, 1,5-dichloro 1-cyclopentene is, in fact, the name of this structure. So be very careful with this type of ring structures because they can give you really difficult cases like the one you see right here. All right, one more example to top it off. We have a cyclohexane structure, and this has 4 substituents altogether. So let's name the substituents. We have a bromo substituent, we got a propyl substituent, there's a cyclopropyl substituent, and of course we have an isopropoxy substituent. Okay. Alphabetically, bromo comes first, then cyclopropyl, then isopropoxy, and finally propyl. Now, in terms of the numbering, you probably want to give the lowest number to the substituent that has the alphabetical advantage, in this case, the bromo. And we're going to work our way clockwise as well as counterclockwise to see what happens, right? So clockwise, we have the blue segment. Counterclockwise, we have the red segment right here. And if you arrange everything alphabetically, bromo, cyclopropyl, isopropoxy, and propyl, in the red scheme, you have the following numbers: 1, 3, 6, and 4 cyclohexane, right? So don't forget to name the parent molecule at the end. If you choose the blue scheme, then you end up with 1, 5, 2, and 4. Okay, so here there is no functional groups. You have to base it on the substituents. 1 turning into 1, no difference. 3 turning into 5, that's bad. That's becoming higher. 6 turning into 2, that's good. It's becoming lower. 4 is still 4, so that doesn't change anything. So you got one bad case and one good case. This is a neutral situation yet again. So now we need to pick the number that has the lowest value first. And 1 and 1, well, they're the same, so that doesn't tell you anything. So you move on to the next value. 3 and 5. 3 is in fact lower than 5, so guess what? The red scheme wins in this case. All right, so this is kind of the trick. Choose C1 to be the one that contains the substituent that appears alphabetically first, and that will help you out. This is in the absence of functional groups. Functional groups always take priority, but if you do not have functional groups, go for the substituent that alphabetically comes first in the name. All right. Now one more thing I'll do is I'll make a little change. I'm going to put 3 double bonds here, turning this into a benzene ring. Okay, so this is no longer cyclohexane. This is going to be benzene, and the whole system goes the same way. This is still 1 bromo, 3 cyclopropyl, 6 isopropoxy, 4 propyl, but instead of being cyclohexane, this is now benzene. And so this is how you will name your typical aromatic molecules. All right, so we have covered most of the bases. We have perhaps one more thing to discuss, and that is if you make a quick little change here. So what I'm going to do is I'm going to take this isopropoxy and I'm going to get rid of the isopropyl segment. In fact, I'm just going to turn it into an alcohol. Now the moment you do that, this is no longer a regular alkane. You have turned this into an alcohol and you have a functional group. So now you're going to have to be on the lookout for the hydroxyl, right? Because that needs to have the lowest value. So what that means is that all these things are going to change. If you name it as such by giving the bromo the lowest substituent, you are toast because you forgot that, oops, hydroxyl is a functional group. So make sure that that happens. Make sure to identify those functional groups, and the alcohol takes priority. So we're going to make the carbon where the hydroxyl is located carbon number 1. And then you go clockwise, you go counterclockwise as well, right? So clockwise on the blue, counterclockwise on the red. And you name them. So you got the bromo at position 2, the cyclopropyl at position 4, and the propyl at position 5 in the red scheme. And cyclohexanol, you could put a 1 in front of cyclohexanol, but it is a little bit redundant because we know that the alcohol is going to take priority in this particular case. If you take the blue scheme, you follow this the following set of numbers: 6 for bromo, 4 for cyclopropyl, and 3 for propyl. And since both of them have 1 for the alcohol, this is going to come down to the substituent. So we look at the top and the bottom names. 2 becoming 6, that's not good. 4 becoming 4 is the same thing. 5 becoming 3 is good. So we have 1 bad and 1 good case. This is neutral. So we look for the scheme that has the lowest number first, and that's the one that starts with a 2. So the red scheme turns out to be the proper name for this structure. All right, so with all this, you have the main components for naming organic molecules. In future lectures, I'll show you how to name even more complex molecules, ones that contain multiple rings within themselves. Okay, so see you in the next lectures.